This video is free body diagrams and force diagrams. Now, before we begin, a small plane traveling at 180 meters per second above the ground at 500 meters above the ground releases a practice missile. Assume no wind resistance. After the plane travels 1,818 meters, the missile lands. Where did the missile land? Ahead of the plane, behind the plane, or under the plane? Go ahead and pause the video, think about it, and give me your answer. Okay, assuming that the plane is traveling at a constant 180 meters per second until the missile lands, the missile will land exactly under the plane itself. Remember, when you have projectile motion, bodies that are in the air, that's only under the influence of gravity, we assume there's no wind resistance. And if that's the case, there is no acceleration in the x direction. The velocity will be constant, and that's why the bomb or the missile will land exactly at the same place underneath the plane that had dropped it. Well, what if the plane's velocity were tripled? Where would the missile land? Doesn't matter how fast it's going. If the velocity is tripled, so will the missile itself. So again, it will land underneath the airplane. Now, what if the plane climbs in altitude as soon as the missile is dropped? Where did the missile land? Well, I can hear an argument either way. Now, let's assume that the x direction, the horizontal velocity of the plane during the climb is exactly the same. In other words, it's constant at 180 meters per second. If that's the case, even though the plane is at a higher altitude, as long as its x component of its velocity is still traveling at 180 meters per second, the missile will land exactly underneath. Last question. What if the missile were thrown straight down with an initial velocity of 10 meters per second? So now we have somebody who's going to throw it down, and if that's the case, it's still going to land at underneath the plane itself. Now, there might be a typo here. It's not going to be exactly at 1,818 meters. I didn't get a chance to change that, but it's still, that's the point is that the missile is going to be below the plane when it lands. Okay, so the number's irrelevant in this case. Today, we're going to introduce what's called free body diagrams and force diagrams. All right, so force diagrams and free body diagrams. First of all, before we get into that, I want to tell you that a force diagram tells you exactly where that force is coming from and where that force is being applied. And a free body diagram is just essentially helping you understand the vectors themselves so you can solve problems. Okay, so there are two different things. We're going to go through each one of them. So we've got a box, and it's on the floor there, and there's someone pulling on that box with a rope, string, or chain. Well, we've got weight, and weight can be represented different ways, so recognize that. But I'm going to go ahead and use f of g, and it's pointing directly straight down. The second thing we can do about with our understanding of weight is that it's always going to be in the center of mass of the object. Okay, for simple objects like a square, it's in the center, or a rectangle. It might be a little bit more challenging, but a triangle, it's in the center, and circle. All of these simple shapes, you know that the center of mass is in the center. Using symmetry, you have the same mass on both sides, and that's really what it is. So for a force diagram, the force of gravity, or weight, is going to be pointed straight down towards the Earth at the center of mass. Well, for a free body diagram, we're going to go ahead and draw the same drawing, or the same vector for now. Now, normal force is applied only when an object is on the surface of something. We've got a box here. It's on the surface of the ground. So the surface is imposing a force on the box, and it's always going to be perpendicular to that surface. So if I were to put an angle here between the normal force and the surface, it would be 90 degrees. And so I'm going to go ahead and put my arrow at the beginning where the surface is, acting on the box, and go straight up perpendicular away from the surface. For my free body diagram, I'm just going to go ahead and draw my vector away from a particle a point particle that I just put in the center, I can simply put a dot there, and all the forces come away from that particle there. For tension, okay, anytime a rope, chain, or something of that nature is being applied, we're going to use the force of tension, and it's from where that force comes from to the direction of that rope, chain, or what have you. In this case, the force of tension. And over here on my free body diagram, I've got that center of mass that I've represented as a point. And I've got all of my forces going away from that point. And then we've got friction. Well, friction is what's called an opposing force. And you can see, though, that there's a force of tension pulling on the rope this way. So that means force of tension is going to be in that direction. And so it's on the surface, opposite of a force and opposite of a motion. Now, keep in mind there are different ways to represent friction. There's a force of static, meaning the object is not moving. You're pulling on it, but it's not moving. And then there's force kinetic, which is the F sub k. That's when an object is moving and you're still having friction there. Now, with my free body diagram, well, there you go. All my forces are coming from that center point, okay, that center of mass that I represented as a dot, and that's the difference. Now, a quick note about force applied. Any generic force that's being applied by a hand or some other box or something of that nature that's not a surface, you can use the term force applied. And that can be a push or a pull depending on where that force is being applied. Now remember, if you need any help, you can always email me at monroe.watson@gmail.com. If you're in the Phoenix area, I can give you tutoring as well. Thank you.